Okay, so this is section 15.8. So in our previous supplement, we learned how to define and use cylindrical and spherical coordinates. So 15.8, we're going to focus on the cylindrical portion of it, and 15.9 will actually be spherical. You see how it's got both of them in the title. That's because it used to all be a part of one section, kind of split it into two sections now. So 15.8 is going to focus on cylindrical. So the concept was in cylindrical, it was basically an extension of polar. It was r, theta, and then z. I want to qualify something there and letting you know that it doesn't have to be z. Okay, one of the variables, x, y, or z, is going to stay either x, y, or z. The other two variables are going to become your r and theta. It's really going to depend on what axis you're going to basically be revolving something around, or not really revolving something around, but what axis the shape is going to be around. So for example, in our first example down here, this is pretty clearly the cylinder is revolved around the z-axis. So that's going to be your standard x, y, z, so it'll become r, theta, z. But if that cylinder was, revolved around the y-axis, then it would be r, y, theta. Hopefully that makes sense. So you're just going to see what axis that your shape is revolving around, or it's wrapped around. That's going to be the one variable that stays either x, y, or z. The other two will become your r and your theta. All right. In general, most of them will probably are going to be around the z-axis, but not always. We just have to make sure we are careful when it's not around the z-axis. All right, so let's look at example 1. It's actually an example from the textbook. A solid E lies within the cylinder, x squared plus y squared equals 1, below the plane, z equals 4, and above the paraboloid, z equals x squared minus y squared. And that is shown in the figure. So really what you can see is that we are talking about all of the space inside of the cylinder between the paraboloid, which is down there at the bottom, up to the top of this thing. So it's basically going to be what's inside of a cylinder, but kind of hollowed out there at the bottom, if that makes sense. The density at any point is proportional to the distance from the x-axis of the cylinder. Excuse me, not the x-axis, from the axis of the cylinder. We want to find the mass. Okay, so we know that the mass is going to be using a triple integral of the density function. So let's see, let's go ahead and define everything. So first of all, it says the density at any point is proportional to the distance from the axis of the cylinder. Well, here's the axis of the cylinder in here, and then the distance at any point out to what would be the edge of this thing is just its radius. So the distance here is the radius, and proportional means we have to have some kind of a constant of proportionality. So what we're looking at here is that rho is k times r, right? The distance from the axis of the cylinder is the radius of the cylinder, and the constant of proportionality, we typically use k for that. So that's what your density function is. All right. This is something you technically could do in terms of x's and y's, but it's going to be so much easier to do in polar. So the z is what's going to vary in green there. Z is going to vary from this function right here up to z equals 4. And they've already gone ahead and done the conversion for us, but I'll write it out here anyway. Z equals 1 minus x squared minus y squared. If you were to simply factor the negative sign out of the x squared minus y squared, you would get 1 minus quantity, x squared plus y squared, and of course x squared plus y squared in polar is r squared. And that's where they get z equals 1 minus r squared. So that's how you would define that paraboloid in polar coordinates. Okay, and that's going to help us because we need to set up our triple integral. So the z portion of this is going to go from that 1 minus r squared up to z equals 4. Okay, again, that's what we have in green inside that cylinder. And then it's based upon r and theta. So what's r going to vary from? Well, r is going to vary from 0. It could have 0 for a radius all the way out to 1. And we get that because that is this cylinder right here. X squared plus y squared equals 1 has a radius of 1. So it's going to go from 0 to 1. And then because this circle pretty much goes all the way around this thing, that means that theta is going to go from 0 to 2 pi. Okay? And the biggest thing is here, so this is going to be kr. Don't forget, the order is important, so it's dz. And then the last two pieces are in polar. And you got to remember that we have to put in that extra r with polar. So it's going to be r dr, d theta. And that was your conversion factor. That extra r was the conversion factor. Unfortunately, all the bounds here are not constant. So we can't just separate all these pieces. But we can at least get through the first step, and then we'll see about if we can separate them. So integral from 0 to 2 pi, integral from 0 to 1. I'm going to take the antiderivative with respect to z. I'm going to multiply the two r's together as we do it. So we're going to get r squared z. Now the k, I'm going to pull the k out to the front of the double integral because it's just a constant, so we can leave it out there. And then we'll evaluate that from 1 minus r squared to 4 dr d theta. So I did a bunch of steps all at once there. I pulled the constant out to the front, I multiplied the two r's together, and I took the antiderivative with respect to z. I'm hoping I didn't lose anybody with that one. All right, so let's go ahead and finish this one off. So let's see, plugging in a 4 for z is going to give me 4r squared. Plugging in 1 minus r squared for z, it's going to give us minus r squared times 1 minus r squared dr d theta. Now, hopefully you recognize that I've only got r's left. So I can actually separate this one if I want to at this point. So we're going to have k integral from 0 to 2 pi of d theta times integral from 0 to 1. Let's see, distributing that r squared into the parentheses is going to give me a 4r squared minus r squared, so that's going to be a 3r squared. And then it's a negative r squared times another negative r squared, so that's plus r to the 4th dr. Okay, and at this point, I am assuming that we can see and do these things pretty well by now without having to write every single little step. I'm hoping you guys can see the algebra and stuff there. Okay, so we're going to get, let's see, antiderivative of k integral 0 to 2 pi d theta is just going to be theta from 0 to 2 pi. That's always going to give you 2 pi. So it's going to be k times 2 pi. And then let's see, we've got the antiderivative of 3r squared is going to be r cubed plus 1/5 r to the 5th from 0 to 1. So we get 2 pi k. Plugging in a 1, we're going to get 1 plus 1/5. Plugging in 0 gives us nothing. So it looks like, let's see, 2 pi k. 1 plus a 5th is going to be 6/5. So we're going to get 12 pi k over 5. That is going to be the mass of whatever the region that actually lies in between that paraboloid and the top of that cylinder. So as you can see, the mass is dependent upon that constant of proportionality k. So, and the constant of proportionality is dependent upon the radius. So the bigger the radius, the bigger the overall value of this thing is going to be, which makes sense. Your mass should be bigger with a bigger space. All right, let's go ahead and do the next example. So sketch the solid whose volume is given by the integral and evaluate the integral. Okay, so it says this particular thing gives us the volume, and it gives us the volume because there is no density function. There's nothing in there as a density function. You might look at that and say, well, wait a minute, what about the R? The R is a part of the conversion factor for the polar. So that's actually not a part of the density. The density function is 1, which is why we're finding the volume, or this thing gives us the volume. But let's see, it says it wants us to sketch that. So the first thing we might want to do is just go ahead and write all of our bounds out. So Z here is the innermost one. That goes with this first one right here. So Z is going to range from R to 4. Theta is the next one. So theta is going to go from 0 to 2 pi. And then they put R last, and the order of theta and R doesn't usually really matter. But R is going to range from 0 to 4. All right, so whatever this thing is, we know it's circular in nature. We know the radius is going to go from a radius of 0 out to 4. And Z itself is going to range from Z equals R to Z equals 4. So let's see if we can sketch that. So it is going to be something around the Z-axis because that's the innermost piece. It's the other variable that's left. Z equals R. Well, Z equals R is a linear function. So if the radius is 1, Z is 1. If the radius is 2, Z is 2. And so on, all the way out till I get to Z equals 4. Z equals 4 is a flat plane. But I know that it's got to be circular in nature. And I get that from this part. And the radius can only go from 0 to 4. And I get that from this part. So that tells me up here at Z equals 4, I'm going to have a circle with a radius of 4. And Z equals R is going to be linear. And if Z and R are both 0, then it's going to start down here at the origin. So what that tells me is everywhere along this thing is going to be linear, which means when it hits the edge, it's going to be a cone. Let's just double check to make sure that that looks right. If you were to make a projection down into the XY plane, the projection down into the XY plane would be circular. And that's what this part is right here. That is your polar projection down into the XY plane. Okay, theta goes from 0 to 2 pi because it's a circle, and the radius goes from 0 out to 4. And that's exactly what we've got there. And then Z itself is going to vary from R up to Z equals 4. So you would get a cone from this thing. The easier part actually is, other than this, after the sketch here, is actually just solving this thing, because that's probably the easiest part since it was already set up for us. So let's go ahead and figure out what the volume of this thing is. Now the question is, do we really have to do the integral? We do not. It is asking us for the volume of the solid which we evaluated here. It's a cone. The volume of a cone is 1/3 pi r squared h. And do we have all those pieces? Of course we do. The height of the cone is 4. The radius is also 4. So the volume is 1/3 pi 4 squared times 4, which is really 4 cubed. So 4 times 4 times 4 is 64. We get 64 pi thirds. And if you don't believe me, you can certainly do the triple integral and you will get exactly the same thing. Now, obviously, had there been a density function on this one, it would have been different. We would have had to have gone ahead and done the integral. But that's it. So there's sometimes if you get a nice geometric figure where you know how to find the volume, you don't actually have to do the entire triple integral. All right, let's do one more of these things, and then we'll probably come back with a second video. All right, so evaluate the triple integral over e of the square root of x squared plus y squared dv, where e is the region that lies inside the cylinder, x squared plus y squared equals 16, and between the planes, z equals -5 and z equals 4. All right, so the sketch of this actually won't be very difficult. That's a very easy cylinder for us to sketch. It's just going to be a cylinder around the z-axis with a radius of 4, but it's going to go from z equals -5 to +4. The good thing is those are flat planes parallel to the xy plane, so this really should not be very difficult. We're going to say that right there is the top. It's going to go all the way down till z equals -5. So that's -5, that's +4. It's got a radius of 4. So there's a pretty good sketch for us. All right, but it does say to evaluate it. Now this one we actually have to do the integral because we actually have a density function, square root of x squared plus y squared. But again, we're going to want to change this into cylindrical coordinates. So we're going to have z, r, and theta. So let's see what we've got. Triple integral. Okay, the r and the theta part should be easy. I like to do my r in the middle, but it doesn't really matter. So theta is going to go from 0 to 2 pi since it goes all the way around the circle. R is going to go from the center out to the edge, out to the most part that r could be, which is going to go 0 all the way out to 4. And then we have to figure out the z. Well, the z is just going to go from -5 to 4. Okay, all those things are constants. Unfortunately, we don't just have to find the volume. Otherwise, this would be really simple because it'd just be the volume of the cylinder. But we are going to do the square root of x squared plus y squared. Now, what is the square root of x squared plus y squared? Well, if you say that z equals, not z, I'm sorry. Well, I guess you could technically. But the square root of x squared plus y squared in polar is going to be the square root of r squared. So that is the same thing as the square root of r squared, which is r. So we're going to take the integral of r dz and then r dr d theta. So now at this point, we can separate all these things and do them completely separately. So let's see, we're going to put theta on the outside. So integral 0 to 2 pi of d theta. Next one is r, so it's the integral from 0 to 4 of r squared dr. And then the next one is the integral from -5 to 4 dz. All right, I am assuming that you, again, know that the integral of 0 to 2 pi of d theta is always 2 pi. Because if you remember, it's just the integral of 1. So you just literally take the bounds and subtract them. That's what you're going to get. Same thing's going to happen with z. It's the integral of 1, so it's really just the difference in the bounds. 4 minus -5 is 9, so that's going to give us 9. And then we actually have a little bit of work to do with the r part. It's going to be 1/3 r cubed from 0 to 4. Plugging in 4, you're going to get 64/3. Plugging in 0, you get nothing. So I get 64/3 times 9 times 2 pi. Let's see, let's simplify that a little bit. 9 over 3 is going to give me a 3. So let's see, 64, we can either do 64 times 6, or yeah, let's do 64 times 6. So 64 times 2 is 128. Times 3, 128 times 3, 28 is going to be 84, so 384, 384 pi. And that really is a mass in this case because we had a density function. All right, I think that's probably a good place to stop. We could probably get one more in, but let's stop there because the next one takes a little bit of time. We'll come back with a second video.